Okay, hello everyone. We are talking about multi-computation, and we are working towards questions about the science and language design of multi-computation. And looks like first on our agenda today is nest graph with ports. Okay, and so this is now nest. Okay, so this is nest tree with named edges. So like these could be event names. These are descriptions of events. Is that although sometimes in a token event graph, well, let's see, this isn't a token event graph because this is just a single token. We can think about this as an event that leads to a single other token. Is that right? Kind of a minimal form of a token event graph.
This can also be used to model decision trees.
Did you get that stuff from the machine learning people for the decision tree stuff?
We did discuss that with them before designing nest tree.
But have they delivered to you some decision tree examples?
They have a method decision tree, but I don't think they're exposing the actual tree object yet.
You might poke them on that because I just, met with those guys today.
I can get it myself too, because I made a function that turns decision tree object for machine learning to a usual tree.
Great. Feed that back to those guys. Maybe they can just use it.
No, I already pushed it to their machine learning bucket, so it has it. They have it.
But they're not exposing it and they're not documenting it.
Yeah.
So is there a WFR that will do it?
No, but it's some kind of private function, and
I understand that you could expose it with a WFR function and then document it there.
Maybe. I think the idea was to think about it more, to how to better expose it. I'm not sure.
Okay, but as a first step, you could make a WFR for it that exposes it there. So then we can just see how it works. Okay, in any case, let's okay, so what are you explaining here? Nest graph tagged.
Well, so last time you suggested that you be able to do nest graph that returns an association. And Roger pointed out that ports isn't for 13.2. And I believe Nick has this nest graph tagged in the WFR that's similar.
Well, so it seems like there's a question of whether or not it should be a port, like in the graph case at least, whether it should be a port or a tagged edge.
Right. So one thing with the tagged edges is you don't have to have uniqueness for the tags. Right? Each edge can just have its own tag independently, whereas ports are, I think.
Well, is it obvious that ports do have to be unique? I mean, doesn't this relate to the whole symmetric monoidal categories and string diagrams and all that kind of stuff? What is the story of uniqueness of ports?
Well, does it have to do with the electronics? Like in electronics, if you have a port and a plug.
Yeah. No, it was abstracted from that decades ago, Brad.
But more generally, I think I don't understand what the, like, you need some way of, if you had, duplicated ports that were not unique, you would, unless there's only one edge in every port, at which point it's just labeled, my point is that it's only useful to have ports if you can have multiple things going in the same port, which you can only do if they're unique.
Fair point. Although, I mean, actually, to Brad's point about electronics, in modern times where you've got USB-C for everything, I mean, it's kind of a fake because it isn't in fact the same port, because the USB-C, connector has all kinds of logic in it. Maybe I cut you off.
But also it's like, you have 4 USB-C ports and each one of them has a different address, presumably, is a different port.
Yeah, that sounds fine. But, in the analogy with functions, the function arguments have a specific order, and you can't supply 2 values for one particular argument.
That's true. Well,
But you could have that the first and the second argument are permutation invariant. Like the output of the function f of xy is the same thing as the output of the function f of y.
Right. AKA it's orderless or it's symmetric or whatever. Okay, so what's the question here that we're trying to answer in this part? What are we trying to answer here?
What do you think the next step for this is?
Yeah, or one question is if are the ports just going to be extra labels on the edge?
Well, I don't know. I mean, is there a nest graph analog there? This is for nest. Okay, this is nest graph. And what you're showing here, okay, so here you've got an association with unique tags here, right?
Yep.
That syntax, I argue, we should certainly support for nest graph. Now, this syntax where we have a non-unique association-like thing, I'm a little bit unclear what the use case is for the non-unique tags here. Do you see what I'm saying?
Right. Well, I mean, if you think of each element in the nest graph as being sort of a transformation rule, right?
Yes.
And you're basically saying that, which is why I think it makes more sense to do edge tags than ports anyway, because, the edges are the transformations. But you could imagine you could have some sort of either non-deterministic transformation or a transformation that, can produce multiple different states. And so that's why you might want repeats.
I see.
Although it is a little unfortunate because if we support lists of rules, it means that nest graph can't do this. It has to be a different function.
Right.
And I suggest that initially we simply support associations, and you can always hack the thing you're describing by having a different tag. I mean, in other words, if nest graph was extended to support associations, where with the association, it just is adding tagging to the edges, that seems highly useful. Does that seem reasonable? And then we can also have.
Although I think that would preclude using that syntax for ports down the road.
Well, yes and no. I could imagine some option that specifies whether you want, well, okay. Well, you've already cooked that goose up here.
In a sense, I mean, nest tree is a little different from nest graph, right? Like trees are ordered, whereas the siblings and graphs, I don't think are required to satisfy any ordering.
Well, okay, so let's look at what would happen. Okay, so
Even the list case is different in nest tree.
Okay, let's look at token event graph, which is a generalization of nest graph, is it not? Do we have the summary of last week's meeting here, please? We said we always need those.
I'll pull it up right now.
Okay, because that's what we need to have. In last time we talked about this notion of subset, of a transformation in which you are picking up subsets in the way that token event graph is doing. Am I right?
Yeah.
Yeah.
Subset tuples, so on.
Yes. But so one thing we need to do is generalize nest graph to the case. So nest graph is the case of one to many, basically. At every step, it's one to many, but unlike a tree, it's one to many tagged only by the identity of the state, which could be equivalence to other states. Am I making sense?
Yep.
Okay, so then there's a separate issue of the token event graph. Now notice that you know, these edge tags are really events. Am I making sense? And
Yeah.
by the way, this is surely the wrong way around. This is surely just the wrong way around. This should say the event A leads to f of x, right? This is the wrong way around. Am I making sense?
Yeah, no. As I said last time, I was thinking of this arrow as labeled.
I
So you
understand. I
can
understand.
you can change this head in the
Yeah.
case you actually want an arrow there. You can change the head.
I'm sorry, I don't understand that.
It's like if you want an actual arrow to be an output from your function, like an actual rule.
I understand, but I don't think
But
we should
that's a
do it
different
this way.
issue, I think.
It's a different issue. Okay. Bottom line here. Let's implement in Nest Graph a version in which we have associations. Now, the only question is, in that association, there are three things that the key could mean. One thing is it could be a port. Another thing is it could be an edge tag. And another thing is it could be some kind of event type thing. Okay, so maybe we need a function other than Nest Graph that for which what we're defining is this event goes to this output. So in other words, let's imagine.
Shouldn't I mean, couldn't an edge tag represent an event?
Yes, it could potentially, except that one event could have multiple outputs. That's the other
Well,
degree.
but if we're supporting things like that, and we also want to presumably support things like one event having multiple inputs, now we're getting into stuff that really doesn't make a whole lot of sense for Nest Graph and is getting more into some sort of general multi-way system function.
Yeah,
where I think a while ago we talked about what the relationship between Nest Graph and that multi-way system function would be, and the basic idea was that we'll have some complicated multi-way system function that'll do all those complicated cases, and Nest Graph is the simple subset.
Right. So fine. So then let's agree that Nest Graph. Okay, so the only issue here really is in this case where we are mapping to an association. Okay. Is what we're doing to tag the edges, or is what we're doing to do something where there is a future kind of this isn't right anyway, because in the world of ports, each edge goes from one node with a port to another node with a port. Okay. So
Yeah.
here, what's that?
Yeah, so we have to get the output or the input ports too, right?
Yes. So this isn't in fact enough to do that with ports anyway.
Yeah, and I think it makes much more sense, if basically the way Nest Graph works is you give it several functions. You're not giving it several, like.
Yeah, you're not giving
Right,
it several edges that go port to port.
Yeah.
But
So-
the tag could be port to port.
It could be.
You mean you could have
generalize the tag.
Yeah.
Yes, that's a reasonable thing to do. That's right. That tag, but with a generic tag without decoration. I think that's the way to develop this. I think that's the way to get this in the end, is that you're right, that tag becomes a port to port. It's a port mapping, that eventually this becomes Nest Graph goes to, and this becomes port mapping, blah to blah.
Wait, I don't understand that at all. So that's basically saying that it's going to have a port called A on both the input vertex and the output vertex.
Well, no, I'm saying
and then it's gonna
A1,
go from.
the port A1 on the input vertex and the port A2 on the output vertex.
I see. So you put that instead of it, and if you give it this special port mapping thing instead of an edge tag, instead of anything else, it'll make those ports.
But if you specify it explicitly, you can get a collision on the A2 input port.
Sure, you could.
Which I don't think we would want.
I'm not sure about that. I think
unless are there going to be two distinct.
We don't know. That's.
I mean, I think if you're doing manual port mapping, you should be allowed to. The whole reason you do this as opposed to just edge tagging is because you want to take advantage of some kind of collision.
Let me make the following point: is that This is action at a distance because this nest graph here, another piece of the nest graph somewhat later could go from the node that is defined here to another node and could reuse that port, unbeknownst to you, so to speak. In other words, the locality, it's not just local information that's needed. It's what else feeds into that. Because the A2 port on the destination node was just used.
Right.
Some other use of the same destination node, the same f of x destination node, could also use the A2 port somewhere else.
That's
So I
what
don't know exactly how
what
that
I'm worried
works.
about, because
Well,
I'm
I know, but
thinking about a port graph that does a little bit more work than what directed acyclic evaluate can do.
well, does directed acyclic evaluate have ordering of arguments coming into a node?
No, so all the ports, all the input ports in directed acyclic evaluate are effectively the equivalent, unless you make an extremely complicated vertex function. But
Okay,
by-
so each function is effectively orderless then. Each evaluation function at the nodes is effectively orderless. Is that correct?
in its most streamlined interpretation. I mean, you can always hack it to do a bunch of different stuff, but usually
All right.
orderless.
Who understands string diagrams well enough to comment on the relationship between this and that? Nick,
So
understand those things?
it's like the question is, why are we naming ports and not wires? If you want to compare it with string diagrams, because string diagrams usually it makes sense to name a wire, and then your process or whatever the object represents, like a box in your string diagram, have a bunch of ports that connect to those wires. It's like
Okay, but
you have unique wires, and you only specify which wires share with.
okay, so that's exactly what we have with this association. We have name the wires.
Yeah.
And that's not confusing. I mean, that's because the association, among other things, forces at least the output wires here to be, well, I mean, yeah, to be unique there. We could reuse the A tag, and in fact, this nest graph will reuse the A tag all over the place. Is that problematic, Nick?
No, not necessarily. In string diagrams, if you have a bunch of things with the same wire connected to it, you create like a spider that acts like a hub. It's like you have multiple wires coming to that spider and coming out of it. It's like a special node that I just created for this wire handling.
Wait a second. What are you saying?
It's like when you have a wire, right? If it's just a single wire that comes from some box and comes into another box,
Mhm.
just one out and one out, it's a simple wire. But what if you have multiple boxes having an output with the same named wire, right? You have to have a wire that have more than two ends, right, connected. So you have to create some kind of hub where these wires come together, so that this hub have now these multiple wires coming out of it.
So wait a minute. Do you want to show an example, or can you describe how?
I think I showed it last time with the diagram processing.
Okay.
Let me find this link again. So it's with the Penrose tensor notation. So we go there, and the example is the scope in the scope tensor notation.
Okay. Explain.
So you see, it's like you specify with your tensor notation a name of like a names, like your psi process has a named wires out of it, coming out of it. G process have some input and output, right? And they
Okay, but
have
the fact that
the
these
name.
names, hold on a second. So this name could as well be a tag on the wire. It doesn't have to be, the fact that you've labeled it at the position of the box, making it look like a port, is irrelevant. It's really a name for the wire.
It's a name of a wire. Yeah, it's basically the same thing.
Okay.
And so in fact that you see multiple A's, those are actually different A's, because if you actually look at the code that created it, you have A1 and A2. So they're different A's.
Okay, but the A's on this wire are the same A. Is that
Yes.
correct?
Yeah.
Okay, so now what's happening here at this is a place where two A wires. No, I'm totally confused. How does this, wait, I can't even follow the arrows.
Yeah. Well, basically, when you have a circle, there are multiple wires coming into it, but it designates the same named one. So it's the same B there in this circle that you're pointing at.
But so what you're saying is, in these graphs, what could happen is that there's a thing tagged with B, but there are multiple things tagged with B that all land on the same node, correct?
Yeah. So
Which is not a problem if we're doing it with edge tags. It is a problem if we're trying to do it with ports.
I guess. Yeah. So you either restrict yourself that there's always only a single input and output for each unique port, or you have to create this kind of hub. I don't know.
Oh, are the hubs the circles there?
Yeah.
Sorry, what? Explain the hubs again. So I mean, either what you do is you just have multiple edges coming in that are all tagged as B edges, for example, or you aggregate the edges and bring them into a single node, right? So in the case of tensors, you typically want to aggregate them because a tensor doesn't just suddenly sprout more legs. Although I don't know what that aggregation actually means. You know, how do you do that aggregation?
Well, those circles are exactly a special kind of tensor, right? Because the whole diagram has a tensor representation.
Well, what is that tensor? What is the thing that combines those? Is that some kind of contraction, or what is that?
Well, you could basically all of them, if you have n legs, you just sum over like different, I don't know, I can show you, I guess. It's just a very simple form of a tensor. Like you give me n, how many legs you want.
But that's a contraction, basically. It's saying the same index is repeated twice, and this is some kind of summation convention contraction. Is that correct?
Oh, by itself, it's nothing is contracted here. You want to create a tensor that have that is rank 3 here, right? It's a rank 3 tensor, this circle.
Mm-hmm.
By itself, nothing is getting contracted. You just have a special form that makes sense for the street diagram case.
I'm a little confused, but let's make a proposal over here and just understand what the consequences are. Okay, so I'm suggesting that we simply generalize nest graph to that if you put an association on the right-hand side here, that generally nest graph has a list here. That we already know. That's ancient history, right? But if it is an association, the keys in the association give but by the way, Kristen, the way you're sending this is not working. You have to send it. If you want to send it, I guess you can send it by email to me, but it's not working to send it like that. Okay. Okay, so look, bottom line here, we're going to generalize nest graph. Who deals with the nest graph code base?
Charles.
Maybe it should be taken over by you, Ian. Okay, why don't you look at that, please?
I'll talk to Charles.
Yeah, I think we should take it over with this group. Okay, so then we will generalize nest graph to do edge tags like this. Make sense?
Yep.
Okay.
Okay.
And
Can
then
I throw out an idea here?
yes.
Well, if you're going through this nest graph iteration, then and you discover a new vertex, you automatically, if you're just assigning numeric labels to the edges or to the ports, when you discover a new vertex, you could say, oh, that's the first one. And then later on in time, you're still doing the iteration. If you return to a vertex, you can say, okay, this is now plugged into the second one, and so on and so forth. The only problem with a scheme like that, which will basically give you all the input and output ports, is that, well, maybe at some time during your nest graphing, you have two edges that are going into the same vertex, and then it's at the same time, and then it's ambiguous how you would order them.
I'm totally confused. I mean, you're saying with nest graph, you are, you're generating edges.
Yeah.
And at the beginning, some new node is created because it is the thing that came from the right-hand side of an edge, so to speak, the end of an edge. But that same node reappears later because the same payload got, you use the same payload later. So more things then return to that node.
Or, yeah, or possibly it's a different function, but you somehow ended up at the same node.
Well, I understand
What I'm basically
because an
saying,
equivalence function ended you up at the same node. The thing equivalents down to the same expression.
Right. Yeah.
And since the nodes are labeled by expressions, you got to the same node. I agree.
Yeah, and then what I'm saying is that order of discovery can basically be in a very simple scheme, can be identified with the port input port ordering.
Yeah, I understand that. I don't think we should do that. I think the order of discovery depends on foliations, depends on traversal orders. It's a total mess. See what I'm saying?
Well, yeah, but I'd also advocate that if we're trying to make it something that works with the multi-way systems, that we actually try to record the foliation information as we're generating these things.
Okay, but it's a different problem. Okay, nest graph is not currently doing foliations. Nest graph is going all the way, so it doesn't really care. Sorry, no, I should say that differently. It has a very simple foliation scheme. Right? It has a very simple scheme where it's just saying, I'm just going to add as many edges. I'm going to add n edges. So in other words, in this number n here could be a front. See what I'm saying? Right now, it's just a pure cosmological rest frame gone a certain number of steps. Do you see what I'm saying? There's no reason why. Do people understand what I'm saying here? Do I need to repeat? Okay, can somebody tell me what I'm saying? Can somebody repeat
N is
that?
the maximum value for whatever the foliation is.
It is the number of edges that you go, 1, 2, et cetera, et cetera, et cetera. You are going, that number of applications of the function. That's what that is, right? It's the count of the number of applications of the function, and you will be applying that count everywhere, right? Which is a particular foliation. It's not the only foliation. We could do something completely different. We could go depth first. We could be applying the function over and over and over and over again on this left-hand edge. See what I'm saying? Ian, do you understand what I'm saying?
Yes.
Okay. So we've got a tree traversal order right now, but what we need, and we've discussed this about 20 times, is we need this, graph foliation, description. We do not have that right now, right? And that is going to be hard to produce. I think what we should do is go ahead and implement nest graph as nest graph has been defined with a single integer there. Subsequently, we can change that single integer to be a structure that represents a different foliation. Does that make sense? Hey guys, wake up. Come on.
Well, I don't think I don't know if it is really as that difficult to add the foliation in. It's just, say you're going through the nest graph and you rediscover a vertex, then its foliation level needs to be updated. That's it.
What do you mean?
Well,
that's not enough. That's not enough to give you. What you're describing is all possible, reference frames, metrics, et cetera, et cetera, et cetera. There's no way you can describe that by just giving, 2 integers or something. It's complicated.
But no, I don't think it's that complicated. I think I could program it pretty easily, actually.
No. You can't specify it. It is the complete story of describing reference frames in space-time, and you are not describing it. It's not, quotes, easy to program.
Oh, well, I mean, if you're worried about the infinite extent of every graph, but if you're worried about just obtaining the minimal foliation for what you've computed so far, that I think is easy to
No, that's easy, but that's not the point. That's not the point. That's not what we're trying to do, right? That's not the point, right? The point is to define, we've got a breadth, but we've been through this many times. This is not an easy thing. I don't think we should tackle it right now. One thing you could do is you could go, do breadth first, you could do depth first, you could do all the things in between, right? And tree traversal order has certain named orderings. Possibly we can have a copy of those named orderings that we can apply to graphs. Does anybody understand whether that's possible?
Well, now I'm really confused because I don't think the foliation depends on traversal order, does it?
Okay. What do we mean by foliation? If you mean which one of these is associated with slice number 1, 2, 3, 4, that's one thing. The microscopic version of that is there are no slices. There's just a traversal order. Okay, slices are already defining equivalence classes, anti-chains, whatever you call them. And
Stephen,
then you go
can you
into
open the page for the documentation for tree traversal order? Look at the illustrations. So in that first illustrations, there's depth first, breadth first, and leaves first. Am I right that breadth first and leaves first are considered foliations, but depth first would not be considered a foliation?
That's correct. I think.
So in that, is that the sense you mean that a traversal order is more general than
Yes.
foliations?
Yes. That's an example. Okay, look, we got to move on here. Let's go ahead. We're going to implement nest graph with associations. So we get this. I think we're going to have something that has a, we need something that allows us to style edges that correspond to particular keys. So I think we want something that is, what should it be called? Key styles or something? What should it be called? Do you understand the option that we're going to want? Is the styling option. Do people understand what I'm saying? We need some option to style the edges here. What should it be called?
Would edge label style work?
Maybe it would. Does
Like,
that?
I think there would be some value of edge labels that says to use the tag as the label, and then you'd control the style.
Well, okay, but how do we do that right now? So, I mean, if I want all 1 tags to be green and 2 tags to be blue, how do I do that in a graph?
Look at edge label.
You can pattern match on the third argument of a directed edge.
Mm-hmm. So edge tag uses the edge tag as the label.
Okay, but that's not good enough. That's not what we want. We want an easy way to, to do this, basically, to color the edges based on the. Okay.
Oh, just your pattern match on the last element of your directed edge.
How do we do that? Like this?
Yeah, you can use a pattern. So you say
what is on the left-hand side of the pattern?
Directed edge, blank, blank, and then you specify a tag. That
doesn't say that here. Doesn't say it here.
This is for edges matching the pattern pat.
Yeah.
And well, it should make it clearer what that means. So somebody should fix this documentation. So you're saying if that says directed edge of blank, blank, blah, then that will work.
Yeah. Which
not the most beautiful thing. I think we want to say that maybe what we want is what would be the analog? It would be something like tag style, arrow, whatever, which, well, or something like edge tag style or something, right? That says for an edge, and we could imagine also a vertex tag style. Am I making sense? Which, or possibly it's vertex tag style rules. Do you see what I'm saying?
Mhm.
Yes.
Well, it could also be a function, like a shape function.
I don't think that's a great way to do it. I think those are horrifying. I think what we want is to say this, and all you say here is like an association that says, or a list that says something like, A goes to red, B goes to green. See what I'm saying?
I see.
Why don't you think about it? Ian, why don't you take charge of making sure that we do something on this?
Okay.
And that will work for graphs in general. A cheap way of coloring it by tags. Am I making sense? Hey, we got to move on here. Is that a yes? Is that a no? Or is that a youth want to think about it? Well, what's the story?
It makes sense.
Okay.
Discuss
So
with Charles.
okay, fine. So Kristen, this is up to you to make sure this happens in some form.
Yes.
You get back to us with what's not happening. Now, okay. Are we on to the next item? Ian, you wanted to share the screen.
Yep.
Okay, go ahead, go for it. Ian, we're waiting. Oh, there you go.
Right. So in the last meeting, towards the end, you identified a few different forms of recursion.
Yep.
Names like time-like recursion, space-like, tree-like, branch-like. And some of them I wasn't so clear on the meaning of. So I went through the documentation that we have for evaluation and kind of made a comparison of
Okay, let's see it.
evaluation. So let's go through that. So there's really only two kinds of recursion that appear in tracegraph. One is reevaluation, which is called iteration, and then the other one is when you have a subsidiary evaluation.
Right. So I think we need to distinguish those two. Okay, we need to distinguish those two.
Yes.
In the subsidiary evaluation, there is
So-
the very space-like case of arrays,
Mhm.
and there is the tree-like case of sub-expressions. Do you understand what I'm saying?
Well, so in both cases, it's you evaluate the head and then evaluate the arguments.
I understand, but the relationship between the evaluations of the arguments, if it is at one level, is a space-like relationship.
Mhm.
In other words,
Right.
those things are all independent. They can all be evaluated. If we think about this in a multiprocessor, assume the code has no side effects, and we think about it on a multiprocessor machine, every element of the list can be evaluated in parallel. Okay.
Right.
But
So
if they are sub-expressions, that's no longer true. Just like in the time-like case, that's no longer true. In the reevaluation case, it's no longer true.
Mhm. Right. So this step one is like space-like recursion through level 1. Don't need to get into attributes.
That's right.
But then after that, then you can apply a transformation rule. And these transformation rules are actually in the evaluator, it's a particular rule and it's applied to the whole expression. You're not somehow traversing the tree and replacing sub-expressions like in replace all. And then finally, iteration, you repeat the whole process.
Well, wait a second. The evaluator, this is the particular depth first evaluation sequence of the evaluator. Okay, this transformation rules thing is generating time-like sequences.
Yeah, I think there's two different kinds of time. There's time from applying a transformation rule, and then there's time from iteration, which is restarting the entire evaluator on the new result.
I don't think that's right. Let me think for a second.
So some of these relationships make more sense in trace graph. So, for a compound expression, this first edge is a recursion edge, right? It's going into the head and evaluating the head, and then the rest of the arguments are held. But here we have non-standard evaluation because there's additional recursion that happens beyond just the evaluate the head.
Look, coming down out of the 1 + 1 semicolon blah blah blah, right, box. The box right above that. The relationship of those edges coming out of that is a space-like relationship, not that one. The second box that looks exactly the same, right? That one there, right? The relationship between those edges is they are space-like related. Those edges. Okay, now this is a weird case because compound expression has non-standard evaluation, which really means that what looks like a space-like relationship is actually not a space-like relationship because it is expecting side effects. But in the absence of side effects, those will be space-like related.
Right. So it's like there's two kinds of recursion that happen. There's the ones from the standard evaluation, which is just the head and arguments, and then there's recursion from non-standard evaluation.
Non-standard evaluation is essentially restarting the main evaluator on each argument. Let's not deal with non-standard evaluation yet. I just don't think that's all that interesting for this. Oh my gosh.
So I wanted to point out with if, not all of the arguments are held, and it actually does not have further subsidiary evaluations. It goes from if to another if, and then just applies a transformation rule.
It's kind of unfortunate that those edges come out in the wrong order there at the top. What is the order in which, what is the, when you draw this thing, there is a temporal order to the different branches being produced on a single processor machine, correct?
Yeah.
On a multiprocessor machine, they might not be. It might not be defined. But right now, and it's super confusing in these trace graphs, it's super confusing that the if is actually before the even queue.
There might be a way to do that. This is using layered graph plot, which is probably sensitive to the order that you feed the edges in, but I'm not sure.
Why don't you look at that and see whether it's possible to get them to actually come out in the correct order? But what's your point here?
My point here is this is a different form of non-standard evaluation from compound expression because it's just coming from the fact that you hold some of the arguments, whereas compound expression holds some of the arguments, but it also has further subsidiary evaluations.
Well, in other words, it reinitiates the evaluator.
And if doesn't.
Yeah, okay, fine.
Here's an example of which is like compound expression in that it reevaluates the or it restarts the evaluator. So the arguments are held and then it has subsidiary evaluations.
Okay, somebody, maybe Nick or somebody else. This restarting the evaluator concept, how does that relate to what we already know about multi-way graphs and token event graphs and things like this? Where have we seen the restart the evaluator again concept?
No, well, I'm not sure the answer to this question, but I see this restarting as because it's always on all the non-standard evaluation. It's hidden under the held arguments, right? If you just focus on the evaluating non-held arguments as a space-like recursion, right? Then it's okay. It's like if your function head holds its arguments, you no longer look at them as it's allowed to be space-like. if it even looks like it, right? You have to
Yes.
feed it as a whole. That's it. So I don't think it's like an.
Well, you're
valid-
saying that they're not independent. It's one blob. It's
Yeah.
not a bunch of independent elements.
Or like the compound expression. Even if it looks like independent, but because compound is holding all the arguments, you have to feed it as a one blob. To apply some maybe replacement rule, then it does some side effects, and then there's a new blob that you have to feed it as a whole again. And you do it iteratively.
Okay.
So last couple of examples here. This is showing the relation that this has with hold attributes. So all of those previous examples had hold attributes, but here you can see that this is a different way of evaluating the sub-expressions. It evaluates the bounds, and then it evaluates the body 3 times.
Yeah, I understand.
Right.
It's controlled evaluation.
Reinitiating its own recursion. Now here's fold list. Fold list does not hold its arguments, but it still has this non-standard recursion happening because the way fold list, the subsidiary evaluations for fold list, it just evaluates the F multiple times until it gets to the end, and then reconstructs into a list.
Okay, let's zoom out for a second. Okay, what you're saying is, go back to that fold list example.
Mm-hmm.
So I think there's this concept of sort of disembodied computation flow, okay, which is very much like combinators, where you could imagine this graph, independent of whether there's a plus there or anything there, it doesn't really matter. There's a certain structure to this graph, and you could imagine that it represents a disembodied computation independent of the actual, elements that are being fed into it. If this is making any sense. In the physics project,
You just mean it's a function.
Yes, but it's not a function of the ordinary kind, because it's a function in which it is defining a computation flow, and as soon as you hydrate it with actual things there, it can do things like produce outputs.
But isn't that what a function does? I mean, the only difference between this and a function is that this is a function where you know exactly what the flow is going to be. Because in an actual function, if it goes down the wrong branch of the if statement, this graph will be totally different.
Yes, but what I'm saying is there's a different kind of function that is kind of like a pure plumbing function, like combinators define, I think, but not quite, but something like that.
You're just talking about a function where you can know at sort of compile time, quote unquote, exactly what the flow is going to be. I think is something that people analyze. I mean, it's something. In much lower level, kind of like compiler stuff, people talk about functions with no branches and stuff like that. They're called like blocks or something.
Yeah.
Well, I hate to input my bias again here, but I was thinking of directed acyclic evaluate, and this is similar, except that I think on this graph we also have port ordering.
Right. Well, that's right. The directed acyclic evaluate is an example of something which is a pure hydration problem. That is, you've defined the graph, and now you start pouring things into it.
Right, but with that particular example, we don't have as much freedom to say that on different nodes, different functions will be happening. And also, it doesn't necessarily have the freedom of saying that on one particular node, the inputs will be treated differently. So, I mean, for plus, it doesn't matter because 2 + 4 and 4 + 2 are the same thing.
Mm-hmm.
But I mean, in the whole general theory of trying to do this with every expression, the order definitely matters, and you definitely have to be able to do different functions at different locations.
Yeah.
So that I guess is an argument in favor of having the input and output ports numbered. on all the graphs.
Oh gosh. I mean, look. Okay, we have to zoom out what we're trying to achieve. I mean, one thing we were trying to achieve. Okay, Ian maybe has more questions or comments. Maybe you should just go through these.
Right. So let me just recap this real quick. So transformation rules is one form of the advancement of time, right? Like you applied a rule to this
Yes.
event or
Yes.
whatever. And then there's also iteration, which is restarting the evaluator. Then there's space-like recursion, which in our documentation we just call it recursion. So then I think
I don't understand the restarting the evaluator.
Are in common from the single way evaluator.
Wait. I don't understand. What is this? Why is there a difference between just continually? The fact that we talk about restarting the evaluator is merely because we have, controlled evaluation, held argument, non-standard evaluation functions. That's the only reason we talk about that. Otherwise, it would just be keep applying transformation rules. Right? The fact that we have this kind of restart.
No, so the standard evaluation order, the first step is to restart the evaluator on the head and its elements. In the absence of any attributes or anything.
I know. I'm saying that
I think the confusion, for at least for me, was that this makes you think you're doing a depth first traversal through the expression, but really that's because you're doing all of these nested restarting of the evaluators.
I see.
Which I think
look, I think there is a confusion because of the recursion through the expression versus the recursion through time. That's been the confusion for a long time.
Mm-hmm.
Okay, but so what's your point here? Is there something else we need to talk about this?
So yeah, here are the things we discussed last time, and I wanted to say how does tree-like recursion fit into this? Is all of this make sense to people? Like we discussed multiple inputs. I don't think we discussed this necessarily because we haven't been talking about restarting the evaluator, but that's something the single way evaluator works. You could imagine having that for a multi-way evaluator. I think these two, are what we're calling branch-like separation, like applying different rules or applying rules to different matches. When in the single way evaluator, you're always dealing with the whole sub-expression.
No, that's not the point. The whole point is there's a difference between replace and replace list. That's the branch-like case. The branch-like is you could have done this replacement versus you actually did that replacement. Do you understand what I'm saying? Right now, we have no branch-like separated things going on, except that things like replace list give us a window into the branch-like world.
Yeah.
Okay.
Right. Although there are some things about, right. I mean, you couldn't take an actual function with down values that makes assumptions about which down, this down value is more specific, so this one will run. You can't just take that and then all of a sudden, use replace list effectively because the logic will just go out the window.
Yeah, that's right. I mean, right. It is not true. There are branches that are just crazy. That were you to follow, I mean, yeah, it's a good point that because essentially it is a set of conditionals that you're waterfalling down a bunch of conditionals. I don't know, that's not really the right term. You're going down a bunch of conditionals and you really don't want the later ones to run, which is a very non-branch friendly situation. I mean, it's, by the way, a situation where clearly you couldn't run it on a parallel machine. If you had, you couldn't do that in parallel. You couldn't, because as you say, Christopher, it simply wouldn't work. right? It would have yeah, I mean, that's one of many, many things. I mean, so look, the evaluator, as we have it, and the functions we built were not anticipating branch-like evaluation. And there's probably a sub-language that can support branch-like things. And I claim that sub-language, and this is where we come back to what Nick was doing, the sub-language where we can do this is not the evaluator. That was case number 3. Remember, we've got 3 cases, right? Remember the 3 cases: function evaluation, replacement rules, and function application, replacement rules, and evaluation. What we're talking about now is case number 3, which is definitely the hairiest of those cases. Does that make sense to people?
Yep.
Mhm.
And so we need to get the other 2 really working well. And I agree, this one is pretty hairy. And possibly not even very useful in the end. I think we should learn about the other 2 first, and then come back to this one. And the only thing we want from this one is the whole trace graph thing. And we will have simplified trace graphs that represent, the function application and replacement rule versions. And those, quote, simplified trace graphs are basically multi-way graphs. Right? The genuine trace graph that works using standard evaluation is something that will be a more complicated version of a multi-way graph.
Yep.
Does that make sense?
It does. And I think, like, basically this is a checklist of things that you would have to tweak from tracegraph to adapt it to these different cases.
Oh,
And
so let's do it.
I agree there's not really much to discuss at this point with it. I just wanted to share.
I think we should just do it. We just want the simplified version of tracegraph that is the thing appropriate for function application and replacement rules. All right. Do you want to unshare here?
Yep.
So let's see. Okay. So let's now go to Nick's lazy Padlet. And so I hope we've got, yes, multi-way nest, multi-way place, multi-way evaluate. Excellent. What I was looking for. Okay, so should I run this?
Yeah.
Nick?
Yeah, okay. Well, there's no actually multi-evaluate yet, because it's only a page.
I understand, but there is multi-way nest and multi-way replace, yes?
Yeah, there's a multi-way replace.
What about multi-way nest?
Also, yeah.
We have that.
We already seen it last time.
We don't have a page for it yet.
I think it's not my guide, right?
Where did this guide come?
There's a link in the agenda, guide page for public implemented lazy functions, with a link to Nick's page.
Which is different from this.
So that guide page has all of the discussed public functions. And this guide page from Nick is what he has currently implemented.
But wait a minute, is this the same as last week or is it something different? This is full of crap again. This is not what we want again. Right?
No,
Remember that?
This is not okay.
This is not, all I want to see is the publicly visible functions.
Those would be publicly visible. What's wrong with lazy range table and array?
Okay, those do make sense. Okay. All right. So what should I be looking at here to actually try this out? I mean, so if I run, let's just understand what we want here. So we say lazy range of 10, for example. What's happening here? Okay. So this has some kind of clever, it has some kind of clever thing which is lovely. Okay, so if I take this lazy list and I say normal of this, I get that list. Okay, so now I could say, if I wanted to, lazy range of infinity.
Yeah.
Okay, and for fun, and by the way, this blob really needs some indicator that gives it a bit more information there. But so now I could say lazy range minus infinity to infinity, and it doesn't deal with that.
Yeah, not this case.
Okay, but it should deal with that, right?
But how would that work?
I'm not sure how it would.
What's the first element?
I don't know. So is it in fact the case that lazy list is a one-way infinite list? Is that right?
Yes, I mean, all we've discussed so far always has a first element and the rest. So it is not symmetric.
Christopher, do you have any comment on that?
I think Christopher had to leave.
Okay. All right. So let's take a look at some of these other things. So what if I were to say, for example, lazy range of 10, and then I would say total of this.
I'm not sure a total is implemented.
Well, but okay, what is implemented? I mean, is that supposed to work, and what should that do?
That may work, but it will return a lazy value. It's not going to return a value.
That's fine, but what's going to be the form of the thing that it returns?
You can try fold over plus over this instead. That should work.
Okay, I don't think that's an adequate. Okay, so that's a thing which you're calling lazy value.
Yes. And if you click it with an option, it will unwrap it as many times as it can.
Okay, but if I were to say fold list, that's a lazy list. Good. Okay, so if I say last of that, what the hell is that? 3, comma, whatever.
Yeah, that I'm not sure about that. That may be a bug.
I'm totally confused. That looks totally wrong. I mean, the true answer is just
Probably does not overload last, so it takes the last of
just-
whatever the
just-
internal structure is. I mean, that's one issue that we have to be very careful that if you do overload functions, we have to catch all the cases, including
so
the
how are we
syntactically
in
wrong
fact
ones.
implementing this? What is it not the case that we've got up values? So to me, it either should do nothing, as in this case here,
We probably will have to make the lazy list an atomic no entry thing to avoid such cases.
Right.
Now, what are these lazy values? What can you do with them?
Well, they're supposed to be used in any occasion when you want to delay your computation. And that's it. It's like if you want to return last of a very large list and you don't want to traverse it immediately. You just wrap.
But eventually you want it, otherwise you wouldn't have asked for it in the first
Yeah,
place.
because that's why you treat lazy value, especially in all the implementations of this function. You kind of unwrap it as soon as you need it. But if you don't need it, you just ignore it.
Yes, but I mean, I'm trying to think of an example where I would actually type it now, but only look at it 2 days from now. So that's kind of, I'm not convinced that we need this.
Sorry, what, Roman?
The lazy values. So, I mean, the question is which functions that consume the whole lazy list, like total, last, max, and so on, should evaluate immediately, and are there any where it makes sense to not evaluate immediately?
It's like if you have a nested list, for example, right? And each of the element is another infinite,
Okay.
right? If you have a way to generate it and you call a lazy drop or last on it, you don't want to.
So you'd have a lazy list of lazy values.
Yeah, you should just ignore all those lazy values.
But then you probably don't need to create them in the first place.
Well, you can. Well, then you're required to think about up, like in advance.
You can always map one of these functions over list, and then it will be evaluated only when you look at them.
Okay, hold on. Go ahead.
Maybe there are. I mean, I just don't see at the moment. I don't see the use case for that, but maybe there is one, and in that evaluator or in that pattern matching packlet that we looked at last time. So I don't. I mean, I don't see a reason for this at the moment, but I'm probably not thinking of a particular case that Nick.
Sorry, what's the this again? I'm sorry. Could you repeat what the this is?
That lazy value that crops up when you do something like fold or total of a lazy list.
You're saying why isn't that just the result?
Yeah, I mean, I don't see for myself a case where I want to type
let me give an
total,
example.
but
let me give an example. Hold on. One definition would be that if it can be stated finitely, just state it. Okay, that would be one position. Now, bug in that position, it is finite, but it is 1,000,000 elements long. See what I'm saying? So one definition would be there is something which can be represented explicitly. There is no infinite thing in it. But now there's the question of when does the laziness evaporate? Does it evaporate when it would give you a 1,000,000 element list, or does it only evaporate when it will give you a single integer? See what I'm saying?
Yes, but I think in those cases, the result should be a lazy list that...
No, which cases? Which cases should it not be a lazy object?
So you have a lazy list with 1,000,000 elements, and you want to find the sum or the max or...
Yeah, I understand. But when does the laziness evaporate? You're thinking it evaporates when you get an integer out, right? For example.
When you get a single value that consumes the whole...
Okay, but you're saying, okay, so your definition is a list, listiness is the thing that is lazified.
Yes.
As soon as there is a single quotes value, it's not lazified. Now, what Nick has argued in the past is that there's a notion of a lazy expression in which there's nothing special about list, but any part of the tree, any pieces of tree can be lazy. Now, I would like to comment on the following thing about an integer. I could imagine, we don't have it yet, that we have a lazy integer which has the feature that not all its digits have been computed. For example, in the number 2 to the 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 2, whatever, it's very easy to compute the last few digits. It's pretty hard to compute the first few. So one could imagine something where any object wants to be pokeable at, but not but not explicitly resolved.
But I mean, in the example of your integer, I mean, another way to represent it would be a lazy list of its digits.
Sure, but it's not what we have. I mean, it's a different structure that we have. I mean, we could say we could replace every expression by nested lists, but we're not doing that. Okay, let's zoom out for a second. One of the things I think is a little odd, hold and release hold are the pair that do that. Okay, here we have lazy And we're overloading normal to release lazy. My guess is that that's a mistake.
Well, I have a function that called release lazy value, if you're interested, which is normal also calls.
I think for now we could call it like release lazy. I'm not sure that that's the right term, or resolve lazy or something. But yes, I think we need to factor out the thing that resolves, because among other things, that resolve lazy function could have parameters that say, hey, wait a minute, just generate a too big failure object if this thing is blowing out, is more than a gigabyte in size or something. Do you get what I'm saying?
Mm-hmm.
I think there's an argument to have a separate function that releases laziness. I think.
Yeah, that's why I have it, and it has some iteration limit.
What is it called?
It's just a release lazy value.
What is it called? Release lazy value.
Release lazy value.
Why don't we just call it release lazy? And why don't we add it to our lazy pack? Who made this lazy packlet list?
I did.
Okay, so did you work with Nick on this, or did you just make it independent of Nick?
I made it separately from Nick, but pulled from his guide page in our.
But Nick needs to buy into this. There's no use to make it without Nick. I mean, this is useful, this is good, except please follow the conventions. Don't use a capital letter at the beginning of these things, etc., etc., etc. But this is good. But Nick, you need to look at this.
Yeah.
Right? Had you not looked at it before this meeting?
No, I haven't.
Okay, I don't understand what lazy, I see. What is too lazy list? What is the relationship between lazy list and too lazy list?
Not too lazy list. It's actually almost the same thing. It's that too lazy list, if you give it a list, it actually turns it into a list. But if you
yeah, I mean, it turns an ordinary list into a lazy list, so it should be called lazy list, but lazy list is taken. So
just too lazy
confusing.
is a little bit more general. It also like can turn.
I mean, you could use the same trick as with association, that the data type is also its own constructor, and so lazy list with a list argument would turn into a lazy list with the same.
I would
argument.
have thought that was the right thing to do.
Well, it kind of works like this already. It's just for some cases you can't use lazy list.
Why?
I don't know if you, because I wanna, there's just like a second argument that I can use for the to lazy list that indicates what kind of lazy list I want to create, for example.
Then
And
we
lazy
need
list
some
is a
other
specific.
function. Do we need something else that does that? Which is just, but don't create a new function, which is just like insane, right? It's got to be one function. Sorry. So make it work, right? Lazy list is its own constructor. If it needs options, you give it options. Does that make sense?
Oh, well, you see, the lazy list is a special, already one kind of a lazy list. And two lazy lists can create a lazy list like objects. For example,
What?
like for pattern matching, I use lazy list like objects that just act as a lazy list.
It's not going to work. I'm sorry. It's not a clean enough design. So
Okay.
let's figure out how to make a proper design. Okay, that does not have two functions here. That's never going to work. Right. So
no, I wasn't exposed. Well, yeah, we can.
Okay, we're trying to actually home in on a design. So that means we don't get to have two different functions that do the same thing.
I mean, one thing I really would like to see at some point is that the basic low-level constructor now called lazy list on the right-hand side, right under the cursor. How does that? How do lazy lists look like?
You mean internally?
Yeah, how do you create one by hand, so to speak? If you wanted to implement lazy table or lazy array, how would you do it? What is the code that creates lazy lists?
The input form.
No, that's okay, fine, we can do that. But I think what Roman is saying is what we need is something that is the lowest level thing that why is this taking time? What is it doing?
I don't know.
What's going on? What the heck did that do?
No idea.
Okay, well, so obviously we need to debug that. What the heck is this doing?
Can I suggest something as well? Maybe.
Go ahead. But why does, wait, why does, okay, this time it was fast.
I know
Okay.
it happens to me, not just for this particular case. Just sometimes it hangs.
What
It's
hangs?
The notebook expressions in general recently. I don't know.
Well, I have to say, I've noticed something similar. I didn't, what the heck is this?
It's like it hangs even before it sends it to a kernel. If it starts to evaluate, then I change the cell, and it's like
Okay,
or
so-
change
so-
goes into it.
Kristen, you need to get that. Actually, we've got a meeting coming up just this afternoon about the speed meeting. Why don't you make sure it gets into that?
Okay, I will.
Into that.
So in fact, that input form, that actually partly answers my question. So the lazy list constructor has the first of its arguments is the first element of the new lazy list. And the second argument is the unevaluated constructor for the rest of the list. Is that true?
Yeah, the first
Okay,
element
yeah.
will hold held.
Oh, it's also held. Yes, I understand that you do it like this, which may make sense. Yes. So
So,
yeah, I mean, this is essentially cons, right? So that was my question. How does this thing actually look like? Because this form makes it very easy to write. I mean, all these constructors, lazy array, lazy table, and so on, are essentially one-liners.
Yeah.
Athena, you were going to make a comment.
Yes. So when I saw some parts of the code, I don't know if it's a good practice, but for example, wouldn't it be better if, for example, lazy range or lazy table called a unique lazy list constructor? Not just they don't just create call themselves in order to create a lazy list, but we have a specific constructor that each one of those calls, so that we can use comparison after that. For example, if I create a lazy list from lazy table, and then I want to compare it from a lazy list that I create from lazy range, I can then compare both of them. I don't know. It was just an idea. I don't.
Right, but the problem is, I mean, that's a problem with these things. The canonical form is not trivially generated. That is, in the case where if I say range of 5, I get a result. I say table I, I5. Those things are clearly equivalent in output. But in the lazy case, I mean, so in other words, what we will be able to say here is range of 5 double equals this, and it's all good. If I say lazy range 5 double equals lazy table I5, oh, what is going on? Why is this so slow?
I mean, to decide whether they are the same, you would have to actually traverse the whole thing. So this is not really.
No, I understand.
It's built into the. I mean, this problem. This is one of the functions that would have to consume the whole thing.
No, I understand. This problem in general is undecidable, whether those two things are equivalent. You know, it's the analog of I've got two, complicated expressions involving trigonometric functions. Are they equal or not? You can't decide that in necessarily infinite number of steps.
Yeah, it's also asymmetric, right? I mean, you can never see whether you can never give true to the question of whether two infinite lists are the same, but you can give false as soon as you detect two different elements. And so
why can't you give true that they're the
because
same?
you never know, right? I mean, you have to traverse the whole thing.
I don't understand. If I say lazy range infinity and I say lazy range infinity again,
Yeah,
do we
then
believe that those two things are identical or not?
I mean, if you look at the structure, then you may see that they are the same internal. Then you could short circuit. But if you are given two infinite lazy lists and you don't know where they come from, and the first million elements are the same, then
you can conclude nothing. Yeah, you can conclude nothing. But I'm asking a question. I mean, is it not the case with transfinite numbers, for example, that, I mean, as I recall, like transfinite numbers below epsilon 0, there is a canonical form, the Cantor normal form and so on. And so does that not translate into some statement about the equivalence of infinite lists? That there is some decidable subtheory of infinite lists where you can determine whether two infinite lists are identical.
I mean, if you know how they are constructed, right? And of course they all need to construct. So, well, I'm a bit confused. I cannot just say yes or no to this question right now, because.
Well, I think you're right that if you've got two constructors, okay, like those two that I just gave, the lazy range infinity and lazy range table I comma, lazy table I comma, if I replace 5 by infinity in both cases, those two things should be, we could imagine doing a symbolic transformation on the code to determine those two things are equal.
Yes, because I thought that maybe, I don't know if that's correct, what I'm about to say right now, but I thought that lazy range is a smaller case from lazy tables. Lazy table is something more general, so I can make when I call lazy range, I can call lazy table at the end, because that's more general. So therefore, I don't have to expand the infinite list in order to see that they are equal, for example.
Well, the implication that you're making there, which I believe not to be correct, okay, is that there is always a canonical form of the program. In other words, the thing you've defined, in general, there might be a short to state program and it's equivalent to a longer to state program. And what you are asserting is that there is a canonical form of the program, that in other words, the range program could be compiled into the table program, and that's good enough. But of course, the table program can then be compiled into into a thing that involves combinators or something. And
yes,
you don't know. And the problem is, in the end, I mean, I think that is, you can never base that recursion, so to speak. In other words, there may be a subtheory in which you can, but in general, you cannot.
Can I give it a slightly more complicated example here?
Yeah.
The range, if you want to generate it from a generating function, is like 1/1 minus z to the power of 2.
Yeah.
And there's a whole theory for generating integer sequences from generating functions, and then how the generating functions can be, for different sequences, can be combined by special operators that stay within this particular set of sequences defined by generating functions. So for example, one of those is the Hadamard product. You could have lazy lists for two of these things, take the Hadamard product of them, and then ask if it's equivalent to a third lazy list. But in order to answer that question, you'd have to know how to take the Hadamard product of the generating functions themselves.
Well, okay, so what you are effectively saying is one thing that actually would be very interesting to be able to do is to take a lazy data structure and make its generating function.
Well, I mean, one thing we haven't talked about so far is the equivalence question and reduction questions and canonical form questions of, once you can have these lazy structures, then, how do you compare them at all?
Well,
and that's probably going to have to be case by case.
No, look, just reminder, we do not have a general way to determine the canonical form of every expression. We do not have a way to compute equivalence for expressions in general. That's not our limitation. That's a feature of computational irreducibility. That's a feature of universal computation. It's just the way the universe works.
Yeah, but we do have a lot of, domains in Wolfram language where we can answer equivalence questions.
I agree. But I think one of the things that you're highlighting here, which I consider to be rather interesting, is the possibility of turning a lazy list-like object into a generating function. That is summarizing in other words, what one's doing is one's algebraically summarizing a program. It's kind of an algebraic summary of the result of a program. Right? And it's a representation of an infinite object algebraically.
Yeah. Or another way that we could do that, like simplifying the lazy, or just describing basically what the lazy list is it if the lazy list or even a lazy tree or a lazy directed acyclic graph is generated by the recursion of some particular iterator, just say what the iterator is. Or the update function, if you call it.
Well, but that's not a canonical form of the update function. I mean, there are many equivalent update functions.
Right. Yeah. But I mean, there's a difference between having a form, which is valid and will get you the correct data structure, and having a canonical form.
I know, but the canonical form is hopeless. I mean, we can have functions that attempt to get you in some subdomains canonical forms, but it will never be generally possible.
Yeah, I think the generating functions thing is one where you can get to a canonical.
No, I agree. I agree with you. So which is why I'm saying I think having a function that goes from a lazy object to a generating function that produces that lazy object is useful. But I don't know how. I mean, in the case of a list, it's fairly obvious how you would. I mean, so essentially in a generating function, what you're doing is you're giving an algebraic way to label, the 6 goes in position 5 or whatever it is, but I don't know where let's say position whatever. I don't know how it's an off by 1, but it doesn't really matter. But this is that z to the 5 is an algebraic way of saying what would otherwise be just put the things out in a list of length 10 or whatever it is. Right?
Yeah.
In algebra, you don't have a way to say I want a list, so you have to code that algebraically.
Yeah, you can also multiply the generating function by x if you're worried about the offset.
Oh yeah, okay, fine. Thank you. Yes.
By the way, lazy series is another one we need. I mean, our series objects are rather clumsy because you always have to decide upfront on the order. So kind of unspecified or infinite series objects and series coefficient lazy lists would also be very useful.
I agree. That's interesting. Kristen, that's for a different group because that's the folks who work on series, which is in the Roger area. The thing that's tricky here, as we start looking at, every function could become lazy. It's not going to work design-wise. How should we deal with this? Should we have a certain set of base lazy things like lazy list and lazy tree? The idea that we're going to have a lazy version of 1,000 functions just doesn't make a lot of sense to me.
Now, in this particular case, I mean, what could happen if you say series of this thing of z, 0 without the 10? It could turn into lazy list, but it could just remain unevaluated as a kind of symbolic series object.
Yeah.
So there's probably very little, there's an interesting connection between unevaluated and lazy expressions, which we should explore at some point.
Well, you're saying that the only difference between a lazy list and an unevaluated generator of the list is that in the lazy list, in this cons thing, it has exposed one element. If it didn't expose one element, it would just be a lazy list, would just be an unevaluated thing. So what's the value of exposing one element?
Well, it's not necessarily exposing it. It's only exposing it when you actually show it. You print it.
Well, but the input form contains it.
Well, you can, but it's not evaluated. Yeah, that's what I'm.
No,
Says.
but look, the question that Roman is raising is the relationship between the purely, what is the difference between unevaluated range and lazy range? See what I'm saying? Maybe there's a different way to think about this in which there is no lazy range. It is simply, or it is a headdress of some kind, lazy of range of whatever. And that's all it is. And it's just a form of unevaluated expression.
And then you have an additional
Question is,
activate.
question is, what can you do to them, right? I mean, if it's like this, then you can certainly also find access 10th element or the 100th element. But there's a kind of iteration and convergence notion in the lazy list that you do the work once, and then you are left with the rest of the object, which also has a first element and so on. So I think that needs some more thought about what the connection, the precise connection is between these two.
Sorry, say that again, Roman.
Well, I mean, in the lazy list, you have a certain expectation that you will normally work with one element at a time, and it's probably always can be considered some kind of fixed point iteration, where you get better and better approximations to something. But if you keep the whole thing around like this lazy range of 6, then what are the operations you can do to that one?
Well, by better approximation to a list, you mean more elements have been produced explicitly, and only the tail is still wagging around.
Yes, I mean iteration in the sense of functions being defined on more and more arguments. And in the infinite case, you would have the fixed point, right? I mean, when the list is fixed point list, when it's infinite, then it is always a fixed point of.
Well, okay, so let's give a specific example. Let's just try it. Okay, so lazy range infinity. What is this speed thing? What is going on?
I know. I'll take a look. I think I don't have it right now.
Is it something to do with this print form? I don't know. You need to figure it out because it's clearly not working okay. All right, so let's take this and we'll say 1 over this squared. And then we'll say, I just want to do your fold plus of this. Okay, so now this is not going to work.
No, but fold list would give you that approximation. Right?
No, but what I'm looking for is pi squared over 6.
Mm-hmm.
So what would it take for me to, to have something which would give me from this pi squared over 6? How do we plumb that together with the rest of our system? Do you see what I'm saying? Nick, do you see what I'm saying?
Well, fold list, that's one idea. Instead of fold, because this way you never have an actual value.
Well, I don't understand. We do have an actual value. The actual value is the sum of 1 over n squared, n goes to infinity.
Oh yeah, well, that's a proof. It proved that it's the same thing. So
no, but the fact is we have a powerful system that can do things like work out what the sum of 1 over n squared is. So my question is, how do we wheel that into this situation? Where in principle, this thing, I mean, it's like, look, I can define a disk, okay? And if I say, what's the area of that disk? Okay, we could say, oh, we just don't know, but actually we say it's pi. Right? And if we say, if we said something like, region union of a disk and a disk with coordinates 0 or half, for example. Okay, and now we say area of that. So you could say, gosh, I can't compute that. I give up. I don't know why it's so slow, but there it is. Okay, so that's something where we've got a symbolic representation of this region of the plane. And then this is a resolver. This is a symbolic resolver of that. And so I can imagine here that there is the notion of a symbolic resolver of this description of some, discrete set, some infinite discrete set.
Yeah, I think it's the same question as how can we turn it into a canonical format and do something clever on it. I think lazy ranges, lazy tables can convert into all the canonical forms. You can think about it.
By canonical forms, you mean things like generating functions and so on?
Maybe, yeah.
Okay.
Well, here in this example, I think you just have to figure out a way to identify plus with sum.
Well, I understand. It's going to be tricky in each case. They're going to be more complicated things. I mean, if I had, I don't think it's going to be trivial. And I think that there are, solving recurrence relations, those kinds of things. That's it. By the way, I mean, that's, Roger and Charles and those guys, Kristen, you should point out to them that we're discussing this, because I think, in a sense, what this is doing is just like if you want to get a sum of the first 100 integers, you could do that by saying sum of I 100, whatever it is, right? Or you can do it by saying, let me generate the list of 100 integers, and then let me do the sum. Let me do a summation over that. See what I'm saying? And so normally for the infinite case, we have not imagined that we could just do something where we are explicitly computing the infinite range and then doing something to it, right? But that's what we're now talking about. Am I making sense?
Yeah, so some kind of compiler. I think it can be done. It's quite tricky. Yeah.
So for example, but now this case,
It's kind of a branch-like question, actually, because let's say that you have the particular functional form. You can either go down one branch of enumerating it, or go down another branch of analyzing it, classically.
Yeah.
So if you already started off one way or another, you sort of have to go backwards or deeper into the code before you can then go forwards again to get an answer.
I say in you, it's like, depends where you stop your unwrapping your lazy range until you actually convert it to your series, to a Hadamard form, right? You can unwrap it multiple times, then you just say that you have a lazy range that starts from 100, and then you turn this lazy range into a canonical form. But you already unwrapped a few values already, and you treat it classically.
Well,
Okay.
with the linear recurrences, you can have recurrence relations, or you can have generating functions, or you can just have big lists of numbers, I guess.
Well, right. But I mean, the recurrence relation is a generator of the type we've got here. That is, we could write this thing here in terms of a recurrence generator.
Yeah.
f of k is equal to f of k minus 1 plus 1.
Yeah. And you can actually go directly from the recurrence relation to the generating function pretty easily, I think.
Yeah, but so there's a class of things that are the sort of algebraically accessible things, which will be a minority of all programs people care about, that can be handled in terms of recurrence relations and so on. In other words, our current recurrence relation function, okay, what's the relationship? I mean, things like lazy table and so on are deeply related to the recurrence relation function. But in a table, you can give all kinds of complicated code as the first argument, whereas in the recurrence relation function, as we currently have it configured, that's, it only really consumes pretty algebraic kinds of things. Does that make sense? But let's zoom out for a minute to what we need to get to here. So, Nick, multi-way nest. what have you implemented there?
So give it a function and initial conditions.
Well, a single function. Yeah, it is a function.
A single function that with multiple outputs potentially.
My favorite one. Okay, initial condition and a number of steps. Is that correct?
You don't need a number of steps. That's the whole point.
Why the heck is that a lazy list?
It's the lazy list because it's you can feed it to multiple initial conditions. So you have to start with multiple trees. But it's just a tree. The
Okay,
first element,
so how do I get the multi-way graph? How do I get 4 steps of the multi-way graph with the most obvious foliation?
well, you traverse it. Well, I don't have like a specific traversal of this thing. The only computation on top of this thing I have is finding a value or a pattern.
Okay, but that's not what we wanted, because we discussed over and over and over again. We have a variety of things. So for example, one thing I want to be able to do is lazy find path, right?
Yeah, that's
do
the only thing I have right now.
I'm sorry?
That's the only thing implemented here.
Okay, so if I say lazy find path of %44, comma, and then I want to go from 1 to 10, for example. Is that right?
No, you're finding a target. So you just feed it a
Not
pattern,
a path then.
just a number in this case.
Okay. So now how do I actually get the path?
Well, just a property of this thing, paths, I think. Or you can just it should be there in the summary box. If it found, yeah. So that's the path.
Well, hold on. So how do I get both the path and the values on the path?
You can take this multi-way nest tree, and if you just part of and provide this particular path there.
No, that's not what I'm interested in. We know what we want. We've talked about this 17 times. We know we need to be able to find the path, the subgraph, all these kinds of things that I already wrote in find replace path like 6 months ago. And that's what we need. Right? Could somebody otherwise just prepare the version of find replace path that I wrote? Hopefully I don't have to do it myself and put it in the frigging function repository so we have something. So we're not doing this over and over and over again. This was not what we wanted, right? We want to be able to find the path. Right? What are you telling me we can do here?
You can take this, extract this path that it found with the property path.
I don't want that. That's not what we want. Look, we went through what this should do, and this is not it.
Well, I haven't worked on it since then.
Okay. Well, so where are we? Okay. Right. We need multi-way nest. We need multi-way replace. We need a version of them that's finite. We need a version of them that's infinite. We've been through this many times. Can we please get these things actually implemented?
Okay.
Okay, really get them implemented, not come back again with them not implemented. You know, really get them implemented. Because again, we know there's lots of complexity in the whole multi-way system function thing. We are trying to simplify that. Do we know how to do that? Do we have to go over that again?
No, we know. It's just a process. It's like I spent most of the time implementing the replace version because it requires all the pattern matching thing.
Okay, fine. Well, then let's look at that version. Should we look at that version?
But it's the same thing. It's just you specify instead of a function, you have a list of rules, and you have a lazy object of the same nature. So it's not going to be
okay. But the thing we've talked about here, again, in this, we are dealing with a single node, a single state turns into multiple states. Am I correct? We're not dealing with the token event graph case, the subsets or tuples case. Is that true or is that not true?
Yeah, not subsets, but multiple positions of the expression that you're starting with.
Okay, so let's just understand this. Okay. So in kind of a standard Wolfram model hypergraph rewriting, type setup. That takes multiple hyperedges. So that is not what you will be handling. That is a subset of the hyperedges in the original hypergraph, correct? And you would not handle that now. Is that correct?
Yeah, correct. That would be some kind of multi-way subset replace.
Okay. Okay, but so multi-way subset replace, which is a reasonable concept, I think, is the case. Wait a minute. So that's where you have a vat of hyperedges, basically, and you are combining ones that sort of, go together,
Right.
which is the token event graph story.
Yeah, kind of. So, but you have a way to splicing them back into a hypergraph because you have a state, which is just an orderless list of hyperedges.
But so multi-way subset replace also has that feature, right?
Sure. Yeah. The only difference from just multi-way replace would be that rules will have a left-hand side that have multiple things in it, because you have to match against multiple hyperedges. Or in general, it would be even not just multiple things in a list, but multiple things in arbitrary expression that have like completely different positions in the expression.
No, I understand. But I mean, if I say something like this, if I say, range of 10 here, and I say X blank question mark prime Q, Y blank question mark prime Q, goes to, I don't know what I say, X plus Y. What the heck did that do? It did multiple replacements here, right?
Well, yeah. The first one is 2 plus 3, and it replaced the 2 and 3. It dropped the 3 altogether.
But it also did 4 here, which must be a 2 plus 2. I don't even know which element.
4 is just left untouched, I think, because it's not.
Oh, yeah, right. Sorry, I was confused what it was doing, yeah. Okay, so this is saying, I don't even know what order subset replace returns the results in.
What do you mean, what order?
Well, what did it just do? So it took 2 plus 3, but some of the primes are not adjacent, right? Let's do the case of like 30 or something here.
Well, what it does, it just finds the first prime, which is gonna bind it to X. Then it finds the next prime, which is binded to Y, and removes both of them from the list, and puts the result where the first one was. And then it finds the next pair. It does the same thing. I think it's not overlapping.
Yeah, no, I agree. I think there's probably an overlaps arrow true option here.
Maybe not.
No, there isn't.
It's confusing because you have to know where to put it. It's like when I've dealt with it with token replace functions and things like that, I always assume that I generate a thing which is kind of homomorphic to the thing that you're matching against. So kind of, if you match 2 tokens here, you should produce 2 tokens back. If you're producing only one thing, it's like the same as producing this thing with nothing. So it just drops the thing.
Well, so you're saying if I say X plus Y, comma X plus Y here.
Yeah, it's not gonna work that way. But I assume it's
Really
kind of splice it back appropriately in the appropriate positions that it matched.
Which is more like subset map, which has that feature that it goes and takes. I mean, that's a kind of bizarre feature of subset replace here. Well, okay, but the point is that the multi-way subset replace, just like multi-way replace, should store much more information about how it gets to the results it gets to.
Mhm.
So that you can extract the graph, for example. Can you do that right now with multi-way replace?
Yeah, because it stores at least a position as a labeled thing.
Actually, sorry, I must have gotten the syntax wrong, because what I really wanted to say here was,
It's a list of rules.
right, so I say x blank goes to x plus 1, x blank goes to 2x, right?
Yeah.
Now, how do I see something from this?
You can ask first and normal, because normal over 3 would be.
Well, how can it be? How can this do anything? It's infinite.
Aborted them.
No, but it's infinite. So I don't understand. How do I see the top few levels on this in this graph? How do I see the equivalent? Because if I do the same thing with nest graph, and by the way, do we have a replace graph? That's the analog of nest graph for replacements.
I don't think so.
Perhaps we should.
We have very many things similar to that. It's like all the multi-way functions is essentially this. The token event graphs and so on.
Well, but okay, that's a separate thing though. Should we have, okay, again.
And you can just make a function to a nest graph, which is just replace of rules. Or
I
replace
see what
it.
you're saying. In the as the function to apply.
Yeah.
And that will work for nest graph because it's not instrumenting things at the level that these other things are instrumenting things. Where, for example, in the case of nest graph, I mean, it's just like if I say nest graph, x goes to divisors of x, for example. And this is a port story as well, because, so let's say I say 15 or something here. What happens if I just do this? Okay. Why does that A give an error and B actually work?
I think it's just one step.
What's that?
I think it's just one step by default.
We should check into whether that's the case. Okay, so this is okay. So my point here, I can pick a different example. My point here is that this is something where there are arbitrary number of output edges from a given thing. Right?
Yeah. Right.
Okay. So again, with multi-way replace, obviously what we want, and we've been through this before, and please, can you actually work on it this time, is to get the functionality that we have for multi-way systems for multi-way replace and multi-way nest. Does that make sense?
Yeah. I'll make some traversals that actually turn it into a graph. You can turn it into a tree, but it's not.
Well, I know, but there's much more to it. I mean, there's
Yeah.
branch-hill graphs. There's tons of different things that right now we have this kind of list of 100 different properties of multi-way system, and we want to simplify that. We talked about this many times before, right? We've talked about the having a branch-hill graph thing that can take any DAG and make a branch-hill graph from it. We've talked about multiple things like that, right? That's what you need to do here.
Well, that's why branch-hill graph is completely irrelevant to the multi-way replacement. It just works for any graph anyway.
I understand, but it all has to fit together, right? So what are the properties of multi-way replace, of the result of multi-way replace, which I don't know what it should be, but I thought it was supposed to be a computation object, not just a random lazy list. Isn't this what we discussed at length? What's that?
Yeah, it's
Okay, so can
now
we
it's
actually implement what we discussed, please?
I get it. I get it.
And make sure that we actually have for next time, make sure we actually have the things that are, properties. We don't need all of them because there's probably too many properties right now for, multi-way system as such. Right. So right, this is what we're trying to deal with. Right. So what we're trying to deal with, this replacing all of this with a nice clean new function. Right. So which parts of this?
Or expressions. More or not multi-way system, maybe multi-way. There's a multi-way function, multi-way operator.
No, we talked about this. It's multi-way nest and multi-way replace. Those are the two things we're going to have.
Yeah, but multi-way system is more than that. It's also string replacement, cell automaton.
I know, but those things need to be folded in a way that, look, it should be the case that, and now I'm very confused by this. I don't even know how this ends up being multi-way. If you say substitution system, how does that become multi-way?
Well, because you can apply your string replacement to arbitrary position in a string.
Okay, but this particular thing with substitution rules, that's kind of a hack, because the truth is the real way. Well, okay, this is where we are confused again, because we need essentially a multi-way kernel for each of these things that will take the full, and that's where we get with this whole event, state decomposition function or whatever it is, event decomposition function and so on, right? That what we're doing is we're taking the whole expression and we're doing something. Okay, so the kernel, right? Kernel of multi-way functions needs to be something that goes from an expression, okay, it has to go to some kind of list of expressions. And by the way, that's the most generic thing, but what we already talked about before is the case where this goes to an association, where those association tags, keys, represent the event names. Am I making sense? This is, I think, the right way to do it. So in the first case, we don't name the events. Right, so we have no causal information. In the second case, we do name the events.
That would be trivial causal information still. The most general kernel is my conversion to hypergraphs. So if you have a simple rule replacement, you just convert it to the hypergraph rule replacement. And then you can make, if you have this conversion, you can make a causal graph.
Yes, I understand. But this is a cheaper version of that. Right, but in other words, the kernel, whatever happens, let's say you've got string replacements there, or you've got Turing machines, or whatever else it is, right? Right now, we've got all these separate functions, multi-way Turing machine, et cetera, et cetera, et cetera. All they are doing in the end is that somewhere, right now, okay, the problem that we have is this. Turing machine, as such, I don't remember how you specify Turing machine state. Anybody tell me how you specify this? Okay, here we go. We don't want the 3 there, we just want this. Okay, so that is one Turing machine state is mapping into a single other Turing machine state. The problem is, in general, we want a single state maps to multiple states, right? Just like we have a nest graph, right? So the kernel of this thing is something that maps one state to many. That's in the simplest case. In the more complicated case, where it's a subset version of this, you have multiple, and this is where, again, local versus global multi-way systems come in. In many situations, this is just so complicated. I mean, the local multi-way system thing, the thing has to be re-knitted back into a global state. See what I'm saying?
Sure.
Right. And so the minimal case, okay, so look, minimal case, fully global multi-way systems, where the kernel simply maps one state to many. Correct?
Yeah,
So another case is,
with some labels now and events.
yes, right, with each of the many being labeled by a tag corresponding to an event. Okay, so now we say sort of the local multi-way system version is, I say in quotes, local, because I think this may be related to the global multi-way systems that Jonathan has looked at as well. What we're doing is, okay, so this has a workflow where we go, take a state, decompose it, take a subset
Mhm.
of the elements, replace them,
Yeah.
reintegrate them
Potentially
into the state. Go ahead.
said with potentially multiple results when you're doing the replacement.
Yes, yes, reintegrate them into the state. But this could give,
Multiple states.
right,
And in the latest token event graph, which is, I think, I haven't still submitted. I have this as separate state vertices. And with an additional decomposition function of a state into tokens, and then recombination of the tokens back into multiple states. So it kind of unifies all the local and global multi-way systems in this one
can
umbrella.
you show this? Do you have this? Could you show it? Could you post one?
I could send you my locally submitted function, and there's
Okay.
I think it's documented. And the options, the token decomposition function and token combination function. And you'll see the state there.
Where are you sending this?
I sent you a link in Zoom.
Oh my gosh, this is getting complicated.
Yeah.
Okay. This is the minimal version of a token event graph.
Yep.
Why are there double lists here? What is this actually? What is the initial state?
It's tokens. So you're decomposing it basically immediately.
But what are the
One state, because you can provide it multiple states, but one state can contain multiple tokens. Okay, so it's like,
so in other words, the hierarchy. Okay, so this is in token event graph. We really, this is a, state contains tokens, and it's the tokens on which the events act. Then an event acts on multiple tokens to return multiple tokens, which then somehow reintegrate back into a state. Is that correct?
Yeah. So if you find like some option that shows the actual states, maybe like state vertices. If you go state vertices true, then you have this additional, this light greenish vertex, which represents a state.
My God. Oh my gosh, this is a tripartite graph, basically.
Yeah.
In which we have a notion of assembly.
There's one problem there because it's not clear that that events act on tokens, even though they are. Because
yeah, I understand. But this is really inserting the observer into this picture, because these are really observer stories. The aggregation of tokens into states is an observer story, is it not? So what this is doing, this is like in chemistry where you have continuous measurement, right? You're trying to maintain, oh, I've really got a water molecule that's oriented this way, which in quantum mechanics you shouldn't be able to do. And the hack that people do to do that is continuous measurement. So I claim this is similar to the continuous measurement thing. Does that make sense?
Not really.
Let me try it again. So you understand the continuous measurement hack?
Yeah.
Right? So in other words, if you want to have a water molecule in a definite orientation, the way you do that is quantum mechanics will never give you that. So what you have to say is, well, actually, in chemistry, the environment is continuously measuring the water molecule so that you can use this classical idea. Okay, so I'm claiming that what you're doing here by continually aggregating these tokens into states is that you're continually saying, this is the quantum reference frame, the quantum frame that you're using, quantum measurement frame or something, that you're using to decide what the state of the world is. You could have used a different frame. You could have done the 6 combines with the 12, and that could have been the thing that the observer tries to aggregate together as a state.
I see. Okay. Yeah.
So effectively, by injecting these, state vertices, spraying them all over this graph, you are effectively doing the kind of thing one does in chemistry of doing continuous measurement.
I know. Well, a very complicated analogy, but okay.
Okay, fair enough. But we need to wrap this meeting, unfortunately. But so is it the case here? It seems like we've got the pure multi-way nest, multi-way replace, and so on. And somehow the token event graph thing is another level beyond that. Is that correct? Because the multi-way X functions are all one state. They're global multi-way functions, which have one state to many kernels. Is that correct?
Kinda, yeah. Well, sure, yeah, that's true.
Right. Whereas a token event graph breaks every state into tokens, which are then acted upon. So in other words, in the case of a multi-way nest, the events just decorate the outgoing edges from every state. That's all they have to do. The events never have multiple connections and so on. They are just decorators of the outgoing edges. Is that correct?
Yeah, we as well could just label the outputs.
Yeah,
instead of-
exactly.
Yeah.
Yes, which is what we're talking about in the association version of multi-way nest.
Yeah.
Okay, whereas here, we're saying we go below the level of states, down to tokens. And then we're acting potentially on whole collections of tokens. And then we have this complicated story of decomposing the state into tokens and recomposing the state from tokens.
Mhm.
Now, one of the confusing things is that it appears that it's a very asymmetric process because the decomposing of a state into tokens is something that just happens at one moment, so to speak. But the recomposing of states has this complicated way of picking up different tokens that requires some kind of foliation story. Boy, this is a complicated area. All right, we have more to do, but I have to wrap up here. And it sounds like, sorry, returning to the lazy stuff, it sounds like we still have some pretty major questions about how that should really work. And I think Roman's key question of what's the difference between laziness and non-evaluation is an interesting question. Because in a sense, what you're doing is, one way to think about laziness in the presentation you have right now with Lazy List is it is, holding with a preview. Am I making sense?
Sure, but preview is not necessary for
Well, why
computation.
aren't we just using unevaluated expressions why aren't we using some version of hold as the way of representing an expression that is?
That's why lazy value is essentially the version of hold with some formatting. That's what I call it. It's like there's no different. It's not different for any other symbol that holds its argument. It's just formatted differently. And that's why I want all the functions work on this kind of expressions that just have a head with a hold all, not just a lazy list in general. I was trying
Well,
to.
but now I'm confused by why are we doing any of this stuff? Why is it not just lazy value of range of 5 or something, and that just works? Now, the only case that doesn't work, well, doesn't currently work, is if we were to go up and do, whatever it would be, something like,
Essentially because the range itself is not lazy enough. So I can immediately produces a finite list. But the point that to have a separate functions that does it iteratively one by one.
I'm totally confused. Why isn't lazy value just something that holds its arguments and you just build up these things, lazy range of infinity plus lazy range, 1 over lazy range of infinity, whatever we have. Okay. And then there's some function that resolves lazy value. And we don't need any of these lazy range or anything like that. It's just a wrapper for an expression that makes it a lazy version of that expression. What's wrong with that idea? And all the intelligence is in the resolver of lazy value.
Well, that's essentially my suggestion that when I had to have a lazy thing that looks like parallel, that just converts every function inside of it syntactically to something else, to a lazy version of it, and then resolves it maybe, right? And we called it crazy. So you have like a bunch of ranges and maps and folds inside that can be in principle strict and eager, but if you wrap it with some wrapper like a lazy value, you just turn it into a lazy thing.
Well, okay. I might be recanting on my craziness claim. Because the reason parallelize has never been a very successful function. But maybe this is a better bet. Because the cost of, I don't know. I don't know. I mean, the problem with parallelize is you never know what's going to happen. See, one point here is that as soon as you've got a range of infinity in here, you have no choice but to have a lazy value. Whereas with parallelize, you can always just say, well, it'll evaluate sequentially and it'll be okay. I am beginning to recant on this issue. Do you understand what the design would look like if we just had one laziness function? I mean, if we just had a single function called lazy that wrapped around everything, wrapped range of infinity, et cetera, et cetera, et cetera. And then all we do is we have a resolver for lazy. Do you see what I'm saying?
It still would return a lazy list, right?
No, it would just return a lazy object. Because all it's doing is returning something. It has no structure. It's just a lazy object which might happen to, for its amusement, cache some preview, which could be used for display. But otherwise, it's just an unevaluated expression.
And you could still ask for the first element of it, the rest of it as before, right? But I mean, obviously the range of arguments to lazy would be rather limited. It would essentially be everything that generates a list. So,
well, it could be anything, but it might not resolve in an interesting way. It might just generate a message right now saying, I can't resolve that, sorry. Or I can only resolve it by just doing eager evaluation of what's inside. There are certain things which are poisonous to eager evaluation, like range of infinity. Am I making sense?
yeah, we should think this through.
I think
in a
so
way,
too. And I
in a way, the
apologize.
lazy,
Go ahead.
the lazy lists are always kind of already you commit yourself to a certain way of presenting them or certain way of iterating over the elements, and you may not even have to do that initially.
Why do it? And I mean, then the question is, if I take this and I say, let's say I then say total of 1 over this squared. Okay, then what happens? What does that do? At the beginning, it might do absolutely nothing. It might stay unevaluated. Or maybe the lazy sucks in the outer stuff. So this becomes lazy of total of 1 over range of infinity squared. Okay. And then the work is on the part of the resolving function. So one could say
this could symbolically, this could find out that this is really just that it can figure out that total thing, right? Just like the sum.
Yeah, right. Well, I mean, so there will be some kind of lazy resolve function, which has all kinds of options for what it should try and all this kind of thing. And I mean, lazy resolve could do all kinds of transformations. I'm Nick. I think I was wrong previously, because I think what you're proving by showing these vast numbers of functions and this increasingly complex design is that that's probably the wrong approach.
Okay.
So I think we should think a little bit more about this pure single function approach, where there's just a single wrapper, well, a wrapper and a resolver.
I'll think about it. I'm not sure about the resolver thing, how it would work. So, because the resolver is a little bit different from the original suggestion.
Well, but I mean, somehow it's got to resolve. How do you otherwise resolve lazy of total of blah, blah, blah?
Well, if your lazy thing of you just produce the same thing that it produces right now. You just normal it.
Yeah, but Okay, but then so you're saying normal is the generic lazy resolve. I don't think that's going to work because I think you're going to need many more options and things for the resolver.
And we probably still want to recognize the case where the argument is actually a list, so that things like map, select, and others would work and go inside the lazy.
Possibly, or not. Yes, I mean, possibly. I don't know how much structural information we can expose from the lazy. I mean, it reminds one of kind of like in biology, you know, cells expose certain things on the cell surface. I don't know what we can expose on the lazy surface. You know, how much type information can we expose on the lazy surface? Don't know. I think the type will also end up having to be lazy. I don't think we'll be able to resolve the type to expose it on the surface. All right, lots of interesting things. I have to go, to be continued. Thanks, guys. See you all soon.